You know, in the world of chemistry, figuring out what a substance isn't always so simple. Sometimes, all you have to go on is one single clue, a simple physical property that can end up unlocking a huge mystery.
Okay, so picture this. You're in a lab, and in front of you is a mysterious white powder. I mean, it could be absolutely anything. So where do you even start? How do you begin to look for clues to figure out what you're dealing with?
Well, it turns out that every single pure substance has its own unique signature. It's an unchangeable characteristic that's as distinct as a human fingerprint. And that is our first major clue.
So let's dive in and explore this idea of a chemical fingerprint and see how it helps chemists unlock a substance's true identity.
And hey, this isn't just some clever analogy we came up with. The melting point is a truly fundamental property that scientists have relied on for decades to identify compounds. Why? Because it's reliable, it's consistent, and it tells a story.
Okay, so what exactly is a melting point? And why is it so unique for every different substance out there?
So technically speaking, it's the one precise temperature where a substance is in this perfect state of balance, existing as both a solid and a liquid at the exact same time. You know, think of an ice cube floating in a glass of water at exactly 0 degrees Celsius. It's not fully melted, but it's not totally frozen either. It's in equilibrium. That specific temperature, that's its melting point.
Now here's where it gets really interesting. This fingerprint isn't just some random number. It's a direct reflection of what's actually happening way down at the molecular level.
There are three main things at play. First, you've got the strength of the forces holding all the molecules together. The stronger those forces are, the more energy or heat you need to break them apart. Second is the crystal structure itself. A really organized, tightly packed structure is just way more stable and tougher to melt than a messy one. And finally, there's atmospheric pressure, which is literally pushing down on the solid, helping it hold its shape.
But here's where the real detective work begins. You see, this fingerprint doesn't just identify a substance, it can also tell you if it's pure or if it's hiding something.
I want you to imagine a pure substance as a perfectly built brick wall, right? Every brick is exactly the same, they all fit together perfectly, creating this super strong, stable, and organized structure. It would take a whole lot of energy to knock that wall down.
Okay, but now what if you shove a random bowling ball right into the middle of that perfect wall? It just doesn't fit. It messes up the entire pattern, it weakens all the bonds around it, and it makes the whole structure way easier to break apart. In other words, it melts more easily.
And this is the absolute key clue for our chemist detective. A pure substance has a very sharp, very specific melting point. It melts right on the dot. But an impure substance, nope. It starts melting at a lower temperature, and it melts over a much wider range. That difference is the smoking gun.
So how do chemists actually measure this fingerprint in the lab? Let's take a look at the technique they use.
The whole process is actually pretty straightforward. First, you take a tiny bit of the powder and pack it into a super thin glass tube called a capillary tube. Then you heat that tube up very slowly and carefully. The chemist watches it like a hawk, noting the exact temperature when the very first drop of liquid appears, and then the temperature when that last little crystal finally melts away. That gives you the melting range.
And of course, to make sure this is all super accurate, they're not just using a Bunsen burner. Modern labs use a specialized device, something like a MEL-temp apparatus, which lets them heat the sample precisely and gradually, and gives them a really clear view of what's happening.
Okay, the stage is set. We have our unknown powder, we've measured its melting range, and we've got a list of possible suspects. It's time for the final test to crack the code.
Now this right here is the masterstroke, the really clever part. To confirm the identity, you take a little bit of your unknown powder and you mix it with a small amount of a pure, known substance that you suspect it might be. Then you measure the melting point of that new mixture.
And here's what happens. If you mix your unknown with, say, compound A, and you get a wide, lower melting range, well, that means they're different substances. Compound A is just acting as an impurity. But if you mix it with compound B and you get that sharp, high melting point that perfectly matches the pure substance, bingo, you found your match. They're one and the same.
That sharp, narrow melting range is the final piece of evidence. It's basically a confession from the substance itself. The unknown has revealed its identity. The mystery is solved. Case closed. I mean, when you step back and think about it, it's pretty incredible, isn't it? A simple temperature measurement, something we deal with every day, becomes this incredibly powerful forensic tool,
capable of revealing both the identity and the purity of a substance. It really makes you wonder, right? If just a little bit of heat can uncover a substance's deepest secrets, what other invisible forces and clever tricks are scientists using right now to decode the world all around us?